Hi everyone. Hi everyone. So in our last video, we introduced the idea of a rational function. And so in this video, we're going to be talking more about rational functions, and specifically we'll be focusing on finding vertical asymptotes and wholes of rational functions. So the goal of this video will be to be able to look at a rational function, look at its formula, and figure out just from the formula, without actually looking at the graph, what its vertical asymptotes and wholes are going to be. Okay, so first thing I want to talk about is actually, it might initially seem unrelated, but we'll see that we need to have an understanding of this in order to deal with rational functions. So I want to talk a little bit about some properties of division of numbers. So not functions, just talking about numbers. So there's just a couple of facts we need to be aware of, and we've talked about these a little bit, but I think they're worth restating. So if you have 0 and you divide 0 by any non-zero number, so 0 divided by 3, 0 divided by -12, 0 divided by 0.8, 0 divided by any number other than 0 is always going to equal 0. So an example of that would be something like 0 divided by -7 is going to be 0. On the other hand, let's say that now you have that your 0 is in the denominator. So now let's say that you're taking any number, and we'll see in a moment why I'm not writing any non-zero number, just any number divided by 0. That is always going to be undefined. Right? We know that dividing by 0 is undefined. And so, just to kind of flip around the initial example I wrote down, if we tried to do -7 divided by 0, that would be undefined, right? That would not be equal to 0. It wouldn't be equal to anything. It would just be undefined. If you try to type it into your calculator, you'll get an error. But the same thing goes for 0 over 0. So I want to just kind of highlight that one because I don't think that has come up a whole lot in this class. 0 divided by 0, that is still undefined. You might think that it should equal 0 based on this first property we wrote down, but that's why I wrote any non-zero number, right? Notice here I wrote non-zero. And so 0 over 0 is undefined. Any number divided by 0 is undefined. But if you have 0 in the numerator, and then just another number that's not 0 in the denominator, then the result will be 0. Okay, so now we're going to see kind of how this connects to rational functions. So we'll see, I'll say it this way. I'll say properties of rational functions. Okay, so first thing I want to mention, and this is something that we've already discussed, I brought it up in the last video and we actually saw it at the beginning of the quarter when we talked about domains, is the fact that when is a rational function undefined? Like, what is it that makes a rational function undefined? So a rational function is undefined at x is equal to c, so at a specific x value, if c is a 0 of its denominator, of the denominator of that rational function. So that might seem, it's kind of a weird way for me to say it. This is basically just a fancy way of saying that a rational function is undefined when the denominator is 0, right? Because what does it mean for a number to be a 0 of the denominator? That's just saying that if you plug c into the denominator, it equals 0, right? So I'm kind of using the language that we learned in the last section about polynomials. I'm saying c is a 0 of the denominator, but that's just another way of saying that it's a number that makes the denominator 0. But if we, using this language from polynomials, we'll find that it just helps us say some things a little bit more clearly. Okay, So what happens, and this is something we did talk about in the last video, what happens when a rational function is undefined? Like, what does the graph look like? So if a rational function is undefined at a particular x value, let's say x is equal to c, it will have one of two features. I'll say its graph will have either a vertical asymptote, so we saw what those looked like in the last video, and we'll see more in this video, or it will just have a hole at that x value. So this is, I'd say, if you get nothing else out of this video, this is kind of the most important fact, is that the numbers that make a rational function undefined, those are the places where we're gonna see the vertical asymptotes and the holes. And so part of the point of this video is going to be focusing on how can we tell whether there is a vertical asymptote or a hole? How can we tell which one it's going to be? And maybe just to quickly mention, one other thing that we will also look at in this video is finding the x and y-intercepts of rational functions. So we'll get to that a little bit later. So just to go back to one of the examples that I brought up in our last video, just to really quickly show you an example of what we wrote above. So what would be the zeros of this rational function? So if we were to factor the denominator, that would enable us to see the zeros of the function, right, of the denominator. So if we factor the denominator, we would get x times x squared minus x minus 2. So this factors further to x times x minus 2 times x plus 1. So that would tell us that the zeros of the denominator, right, the values that make the denominator 0, would be x is equal to 0, right? That would come from this first factor. X is equal to 2, that comes from the second factor, and x is equal to -1, right? Those are the values where our function is undefined. And so what we can see in this graph is that we have a hole at -1, right? That matches with this. We have a vertical asymptote at x is equal to 0. And so that would be this, right? A vertical asymptote is when the graph kind of splits apart and it never touches that x value, right? It never touches x is equal to 0. Instead, the graph kind of traces along it. And then finally, we have x is equal to 2. And we can see that that is also a vertical asymptote. So, I didn't tell you yet, like, how we can tell which ones are going to be holes and which ones are going to be vertical asymptotes. That's what we're going to get to next. And so we'll come back to this page and add a little bit more detail under this so that we have kind of a full story of what's going on here. But I want to start by looking at a different example. So the first thing I want to do is I want to figure out, what are the places that this function is undefined? So at what x values is f of x undefined? So if we take our denominator and set it equal to 0, that will tell us, right, what's going on. So we can take x squared minus 4x plus 3 and set it equal to 0 and then factor. So this would factor as x minus 3 and x minus 1. And so this would tell us x is equal to 3 and x is equal to 1. Those are the two places where the function is undefined because the denominator is 0. You could also, by the way, in the last example I did this, I wrote it a little differently, right? I factored while the function was all one piece. You can do it that way too. You can either factor kind of all together, or you can just take the denominator separately and factor it. We'll see that in our next example. Sometimes it is nice to factor it all together. Maybe I'll even do that here so that we can compare it, because we're going to have a similar but slightly different example next. So I think it will be nice to see that in its factored form. Okay, so we're going to have either a hole or a vertical asymptote at these two x values, right? That's what we said earlier. So I want to pull up the graph on Desmos. So on this example and the next one, we're going to start by looking at the graph on Desmos, but then the next couple, that's where we'll start like predicting ourselves whether things are going to be wholes or vertical asymptotes. Okay, so let me just make this a little bolder. So here's our graph. This is the graph of x plus 1 over x squared minus 4x plus 3. So we can see that it has a vertical asymptote at 1 and a vertical asymptote at 3. So both of the places it's undefined, those both turned out to be vertical asymptotes. So let's make a note of that. So vertical asymptote, vertical asymptote. And now I want to look at a similar example and kind of try to see like what is the same and what is different in this example. So again, we're going to say at what x values is now this function is g of x undefined. So same idea. I mean, it's actually the exact same denominator, right? X squared minus 4x plus 3 is equal to 0. So we already know that factors as x minus 1 and x minus 3. And so again, that tells us that the two places where the function is undefined is that x is equal to 1 and x is equal to 3. So same two values where the function is undefined, like same exact as the last one, right? By the way, what's the difference between this function and the last one? The only difference is the numerator, right? So the last example, the numerator was x plus 1. This one, it's x minus 1. But we'll see that that is going to actually make a really big difference in how the graph looks. So I'm now going to pull up the graph of, so this was the first function with the two vertical asymptotes. This is now the second function. So let me get rid of this one for a second. So notice that this graph still has a vertical asymptote at 3, right? It still has this shape. And again, just to quickly remind you, the asymptote is not actually part of the graph. It's just sort of a feature that kind of describes the shape of the graph. So notice I graphed this separately as a line, and it's just to kind of help us get a visual of what's going on. It's not actually part of the graph. So yes, we can see that we have this vertical asymptote at 3. So let's see what's going on at 1. You know, initially it might look like, well, nothing's going on at 1, right? 1 looks fine. But if you actually trace along the graph, when you hit 1, you'll see that, if I can get it to go there, it says undefined, right? Actually at 1, the graph is undefined. So in this case, we don't have two vertical asymptotes. Instead, we have a vertical asymptote at 3, and we have a hole at 1. Okay, so what's going on here? Like, what is different between these two functions that is causing that to happen? Well, I'm going to write just like we did on the last version, right? We rewrote it kind of as its factored form at the top. I'm going to do the same thing on this function. So if we rewrite this as with the denominator factored, well, now we can see that we have a common factor in the numerator and the denominator. So I'm going to go ahead and I'm going to cross those factors out, but you have to remember there's something that we do when we cross out a factor like this, right? We don't just cancel it out and ignore it forever. We have to kind of record that information of what we canceled out. So our original function is not exactly the same as 1 over x minus 3. It's the same as 1 over x minus 3 with the added restriction that x cannot be 1. So what's going on here? Basically, we saw that one of the factors of the denominator, it kind of like canceled out, and one of them stayed. And notice that the one that canceled out, well, that was the one that ended up being the hole. And the one that did not cancel out, that was the one that ended up being the vertical asymptote. So that's going to be the general rule, is if your factor cancels out, it doesn't mean that it goes away forever. It doesn't mean you can just ignore it. There's still an issue there. It's just that it's not as like big of an issue in the graph, right? It's just this kind of little blip. It's like one little point where the function is undefined. And that's really where this domain restriction comes in, right? That's the way of communicating, okay, well, this function is almost the same as 1 over x minus 3. We just have this one little extra issue, which is that there's a little blip at 1. Whereas the one that does not cancel out, well, that you just can't do anything about that. And so that's going to really cause a major kind of change in the shape of the graph. It's going to split the graph apart and cause a vertical asymptote. So I want to show you one other thing. So here I have graphed 1 over x minus 3. So that's going to show up in orange. Notice it looks exactly the same as the purple one, but if I just graph 1 over x minus 3, that function actually is defined at 1, right? So it's not the same function. It looks like exactly the same, but if you actually focus in on x is equal to 1, it's different. So again, going back to the original function, looks the same, but when you hit 1, it's undefined. And so again, that's why it's so important to include that little note of where the function is undefined. Okay, so let's try to summarize what we just said on this initial page. So basically what we said is that so again, remember going back to the beginning here, we were talking about x is equal to c, right? So we're saying that if the rational function is undefined at x is equal to c, it has either a vertical asymptote or a hole. So if c is a 0 of the denominator only, and another way of saying that is that x minus c is a factor right? Those are equivalent. We know that if something is a 0, then x minus that thing is a factor, right? So if you have a number that's a 0 only of the denominator, meaning that x minus that thing is a factor of the denominator only, then you have a vertical asymptote, or I should say f of x has a vertical asymptote at x is equal to c. So going back to our two examples, in the first example, both 1 and 3 were only zeros of the denominator, right? We didn't have any common factor in the numerator that canceled out. And then looking at our second example, that's what happened with 3, right? X minus 3 was a factor of the denominator only, meaning that 3 was a 0 of the denominator only. And so that's why we had a vertical asymptote. On the other hand, if that same number c, maybe I'll do this to kind of separate these out. So if c is a 0 of both the numerator and the denominator, and another way of saying that would be that x minus c is a factor of both, then that means that your function has a hole at x is equal to c. So the vertical asymptotes happen at these places where so maybe let me say one more thing, which is that holes in vertical asymptotes both happen when the function is undefined, right? So they both happen at the places where you're dividing by 0. The vertical asymptotes happen at those places where the 0 is in the denominator only. And then the holes happen in those places where that 0 goes in both the numerator and the denominator. So it's basically going back to this idea up here, right, that any number divided by 0 is undefined. So regardless of whether you have a situation more like this one, where 0 is only in the denominator, or a situation like this one, where 0 is in both the numerator and denominator, in both cases it's undefined. But there is kind of a difference in how that undefinedness looks in the graph. Okay, so I also want to talk about X and Y-intercepts. So what we're going to do is we're going to find X and Y-intercepts for those first two examples that we did. And then we're going to do a couple more examples where we'll find the holes and the vertical asymptotes and the X and Y-intercepts. Okay, so let's start by finding the Y-intercept. So the good news is that for finding the X and Y-intercepts, the method is exactly the same as it is for any function, right? So how do you find the Y-intercept in general? Well, the Y-intercept always happens when X is equal to 0. Right? That's the definition of the Y-intercept. It's when the graph crosses the Y-axis. And so all we need to do is just plug in 0 for X. And so we're going to say f of 0 is equal to, And so you can use either the factored version or the not factored version of the function. It doesn't make a difference. I'm going to use the non-factored version. So we have 0 plus 1 in the numerator. And then in the denominator, we have 0. Sorry, let me just remind myself. Oh, here. It's 0 minus 4 times 0. Or I should say 0 squared minus 4 times 0 plus 3. And so this simplifies to 1 over 3. And so that tells us that the y-intercept is going to be the point 0, 1/3. So y-intercepts are, fairly straightforward. They go exactly the same way as they do for any other function. Okay, what about the x-intercepts? So we'll see that in some of the cases, the x-intercepts are going to be fairly straightforward. I don't know why that keeps happening. But we'll see that there are going to be some cases where finding the x-intercepts there's like one kind of complication. So in general, how do you find the x-intercepts? Well, you do so by setting the whole function equal to 0 and solving for x, right? Because the x-intercepts happen when y is equal to 0. In other words, when the whole function is equal to 0. So we have x plus 1 over x squared minus 4x plus 3 is equal to 0. Okay, so we now need to think about what are the situations where a fraction is equal to 0, right? Because this is like a fraction being equal to 0. So going back to this kind of beginning part of the video, what is the situation where in a fraction, the whole fraction altogether equals 0? Well, that happens when you have 0 divided by a non-zero number. So when we're finding the x-intercepts, what we need to do is we need to figure out where is the numerator 0, and then we just need to double check that that same number does not also make the denominator 0, right? Because if it also makes the denominator 0, then the whole function is undefined. It's not equal to 0. So maybe I'll write that down. So we know a fraction equals 0 when its numerator and additionally not its denominator, right? Because if its denominator also equals 0, then we're in trouble. Equals 0. And so what that means is, like we said, we want to just take the numerator and set that equal to 0. So we would get x is equal to -1. So the only thing we need to check is that that number does not also make the denominator 0. But we already know what makes the denominator 0, right? We already know that the two values that make the denominator 0 are these. And neither of those is -1. So we're good. We're fine. We just want to make sure, and we'll see this come up in another example, that there is no overlap between the zeros of the numerator and denominator. And so this tells us that the x-intercept is going to be the point -1, 0. So again, this really just goes back to understanding those properties of numbers. If you understand how a fraction works in terms of what gives you 0, what gives you undefined, this really isn't like, I don't want you to think of this as a million new rules to memorize about everything. But what I think is really new is the vertical asymptotes and wholes. Like that part is new. But the rest of it is really just understanding how fractions work. Okay, so let's look at our graph. So that is not our graph, that was the second one. So here's our first graph. So we can see that it does in fact have an x-intercept at -1, 0. So that's what we said. And then its y-intercept is at 0, 1/3. So we can see that what we found is in fact correct. Okay, so let's do the other example. So let's start by finding the y-intercept. So the y-intercept is going to happen when we plug in 0, right? So we want to do g of 0. And so in this case, we have 0 minus 1 all over 0 squared minus 4 times 0 plus 3. And that is equal to -1/3. And so in this case, the y-intercept is going to be 0, -1/3. Okay, so what about the x-intercepts? Well, same idea from before, right? We want to take the whole function and set it equal to 0. And then we know that that's going to happen, that the whole function is going to be equal to 0 whenever the numerator is equal to 0, but the denominator is not also equal to 0. So if we set the numerator equal to 0, we get x is equal to 1. However, there's a problem, right? Because x is equal to 1, we already know that that also makes the denominator 0. And so what that basically tells us is that there is no x-intercept, because in fact, we actually already know there's a hole there, right? We know there's a hole in the graph at x is equal to 1, so it can't be the x-intercept if it's also a hole, right? Holes are places where the function's undefined, so it can't also be an x-intercept. So this number is also a 0 of the denominator. So it is a hole, not an x-intercept. So one way that you can kind of think of all of this stuff is that basically if you have a number that only makes the numerator 0, it's going to be an x-intercept. If you have a number that only makes the denominator 0, it's going to be a vertical asymptote. If you have a number that makes both the numerator and denominator 0, that's when it's going to be a hole. And so let's just kind of verify that by looking at our graph. So this is the graph of that function. And we can see that there is no x-intercept, right? The graph never touches the x-axis, actually. And so that kind of verifies that it's not true that there's an x-intercept at x is equal to 1. And in fact, the function is actually undefined. There's a hole that I can't seem to get onto, but there is a hole at x is equal to 1, so it couldn't have possibly been an x-intercept. Okay, so let's do a couple more examples. So both these examples, we're going to do everything. We're going to find the holes in vertical asymptotes. We're going to find the y-intercept, and we're going to find the x-intercept. So if you haven't already, I would really encourage for these next two examples to pause and try it yourself. And then we'll go look together also at the graphs to kind of confirm what's going on. And actually, let me just say one more thing, which is that I'm not going to be asking you to sketch the graphs of these functions by hand. Basically, they just get complicated pretty quickly. There's just kind of more going on than meets the eye. So really all I want you to do is to be able to find the vertical asymptotes and holes, the x-intercepts, the y-intercept. And then, maybe in like a multiple choice format, you should be able to identify the graph, but I won't ask you to be graphing them by hand. Okay, so first thing we want to find is we want to find the holes and vertical asymptotes. And so that's basically the same thing, right, as asking where is the function undefined. Okay, so how do we find the holes and the vertical asymptotes? Well, that's where the denominator is equal to 0. So we get x minus 2 is equal to 0. And that tells us the function is undefined at x is equal to 2. So the next question is whether x is equal to 2 is going to be a hole or a vertical asymptote. So how do we figure that out? Well, we want to also factor the numerator so that we can determine whether 2 is a 0 of the numerator as well. So how does this numerator factor? Well, it's not one of the super easy ones to factor, but we can do it by trial and error, right? So we know that we have 3x and x. And then we know that we need to get negative 10. And so, for example, we could have 3x plus 5 and x minus 2. And that actually does work. So if we multiply these together, we get 3x squared minus 6x plus 5x minus 10. And that matches what we have here. But, maybe instead you would have tried first like 3x plus 2 and x minus 5. Of course, you could try all sorts of different things, but there's not going to be too many to try before you get to the correct one. And so what this tells us is that this x minus 2 actually cancels out. So another way of writing this function would be to say it equals 3x minus 5 with the domain restriction that x is not equal to 2. So this tells us that we have not a vertical asymptote, but a hole. So this function actually does not have any vertical asymptotes. It only has a hole. Okay, so what about the y-intercept? So y-intercept is kind of the easy one. That's just plugging in 0. So we want to plug 0 into this function. So that is going to be 3 times 0 squared minus 0 minus 10, all divided by 0 minus 2. So that's going to give us negative 10 in the numerator and negative 2 in the denominator, and that's going to equal 5. And so the y-intercept is going to be the point 0, 5. And by the way, that shouldn't be too surprising, and we'll see this graphically. And actually, sorry, I made a little mistake here. This should be 3x plus 5, right? Because that's what we were left with. When we pull up the graph, what we'll see is that this rational function actually looks pretty much exactly like this line, 3x plus 5, with the exception of that place where we'll see there's a hole. And so, well, the y-intercept of 3x plus 5 is 5, right? And so it makes sense that we got 5 as our answer for the y-intercept. All right, last thing to find is the x-intercepts. And so that's where we want to set the whole function equal to 0. So we have 3x squared minus x minus 10 over x minus 2 is equal to 0. And then we want to say, well, actually, that just means the numerator should be 0, right? And then once we get our answers, we just need to guarantee that they do not also make the denominator 0. I'm sorry, I don't know why my computer is having so many issues right now. Okay, so we have this. We actually already know how this factors, right? We did that above. So we have 3x plus 5 times x minus 2. And so that tells us that either 3x minus 5 is equal to 0 or x minus 2 is equal to 0. And so that would give us x is equal to 5 over 3 or x is equal to 2. So those are our two candidates for our x-intercepts. So now what we need to do is we need to double check that neither of those also makes the denominator 0. So x is equal to 5/3 does not make the denominator 0, right? If you plug that into the denominator, nothing bad will happen. However, x is equal to 2, that does make the denominator 0. And we already knew that, right? We already knew that there was a hole at x is equal to 2. So this is a hole, so it cannot be an x-intercept. And so our only x-intercept is x is equal to 5/3. So let's check out this graph. So it's this one. So like I said, it looks just like a line, which is maybe a little bit surprising. You see this kind of crazy looking function and it comes out just looking like a line. The reason that it comes out looking like a line is because we saw that it can be simplified, right? And the only difference between this and a regular line is that if we go to x is equal to 2, notice that it actually says undefined. So the function is not defined at x is equal to 2, and we have a hole. And if I compare that to the line 3x plus 5, it looks exactly the same. The only difference is that 3x plus 5 actually does not have a hole, which I can't quite get it to go there. But if you go to 2, it is defined. Okay, one more example. So again, we're just going to go through the same process. So we're going to start by finding the holes and vertical asymptotes, and then we'll find our intercepts. So the vertical asymptotes and holes are going to occur when the denominator is equal to 0. Okay, so how do we solve something like this? So this one maybe doesn't look as clear of how to go about factoring, but we can factor out an x from both of these, right? So we could rewrite this as x times x squared minus 1. So now we're left with something that we can factor, right? This is what's called a difference of squares. So this factors as x times x plus 1 times x minus 1 is equal to 0. And so this tells us that we have 3 places where the function is undefined. So there's either going to be a hole or a vertical asymptote at each of these values, 0, -1, and 1. Okay, so now we just need to see which of them are holes and which one of them are vertical asymptotes. So let's go through kind of this simplification process. So this can be written as x plus 1 times x minus 1 times x plus 1. So we can already see that the x plus 1, that's the one that's a common factor in the numerator and the denominator, right? So this function could be rewritten as 1 over x times x minus 1 with the added restriction that x cannot be negative 1, because that's kind of the place that was undefined that we were able to cancel out. And so what does this tell us? This tells us that the one where x was negative 1, well, that's the one that's a whole, right? Because that was the one that canceled out. The x plus 1 was also in the numerator, whereas these two are vertical asymptotes because they did not cancel out. So we should see later on that our graph has two vertical asymptotes and a whole. Okay, so next up is the Y-intercept. So how do we go about finding the Y-intercept? We just plug in 0 for x. Although we'll see that there is something a little bit different that happens in this one. So what happens when we plug in 0? Well, in the numerator, we get 0 plus 1. But then in the denominator, we get 0 cubed minus 0. And so that's going to be 1 over 0, which is undefined. So what does this tell us about our graph? This tells us that there is no y-intercept. So why would that kind of make sense with what our graph looks like if you're starting to picture it? Well, we already know that the graph has a vertical asymptote at 0, right? We found that up here. And when a graph has a vertical asymptote, that means that it does not touch that x value. And so our graph should not touch the y-axis, right? Because that's when x is equal to 0. And so it makes sense that it doesn't have a y-intercept, right? Because if it had a y-intercept, that would mean that it was crossing the y-axis, which we'll see that it does not. Okay, x-intercepts, we are just setting the numerator equal to 0. So that one's fairly easy in this case, right? We just have, well, I'll write the whole thing out because it really comes from this fact, right? It comes from setting the whole function equal to 0. But as we discussed, that's really going to happen when the numerator is 0. So that would be x is equal to negative 1. But then we just need to check that that does not also make the denominator 0. However, we saw that it actually does, right? We saw that x is equal to negative 1 does make the denominator 0. There's a whole at that point. And so that tells us that this is a whole. So that means that it cannot be an x-intercept. And so what does this tell us about our graph? Well, it actually tells us that this graph has no x-intercepts. So we should see when we look at our graph that it's going to have no x-intercepts, it's going to have no y-intercepts. It's just going to have two vertical asymptotes and a whole. So let's look at the graph. So here is our graph. Has this little piece. When you're graphing these, it's sometimes nice to zoom out because if you just looked at this, you would miss this whole middle part, right? And this, by the way, is why we're not graphing them by hand. It would be really hard to know where exactly this bottom piece fits in. And basically when you get to calculus, you'll learn more tools that might help you graph something like this without so much guesswork. Okay, so what do we see? Well, we have a vertical asymptote at x is equal to 0. And so again, the graph does not have any y-intercepts because it does not touch the y-axis. We also have a vertical asymptote at x is equal to 1. And then the other thing that we should have is a whole at x is equal to negative 1. And we do see that the function is undefined at x is equal to negative 1. I'm just going to, last thing in this video, I'm just going to go back and summarize what we said about x-intercepts in the front page, so that you kind of have it all in one place. So if you feel like you have all this down pat, you can stop watching now, but in case you just want to quickly review that, I'll write that down here as well. So basically what I'm saying is that a rational function has x-intercepts when the whole function is equal to 0. This occurs when the numerator equals 0, but the denominator does not. And maybe just to kind of rephrase that one different way, kind of more similar to the language above, is that the function f of x, your rational function, will have an x-intercept at x is equal to c if c is a zero of the numerator only. All right, so that is it for this video. In the next video, we're going to be covering horizontal asymptotes and then doing some examples of kind of putting all of these different pieces together. So I'll see you all in our next video.